Good morning and welcome to this Maskless Lithography Microlight3D seminar. My name is Tiffany Willoughby and I will be the session moderator for today's discussion. Joining me are Christian Oliver. Christian Oliver is currently Vice President North America for Microlight3D. He has an executive track record with 10+ years of experience in semiconductors. He managed integrated product development companies, including semiconductor and electronics manufacturing fabs, both in Europe and North America. Also joining us this morning is Dr. Cordiero. Dr. Cordiero is sales manager at Microlight3D, where he is in charge of the 2D lithography tools. Dr. Cordiero obtained his master's in science degree in nanotechnologies and nanobiosciences from the University of Burgundy, Dijon in 2010. In 2014, he received his PhD degree in nanophysics from the University of Grenoble and was working on optical properties of 3D self-assembled nanoparticles in the microelectronics technology laboratory, LTM, CNRS. During his postdoc, he developed equipment for controlled deposition of colloidal nanoparticles and maskless lithography. In 2015, he co-founded SmartFace Technology, SAS, a company developing tools for micro and nano fabrication, and holds the position of president and CEO. In addition to his management role, he was in charge of the sales activities. In 2019, SmartPrint Technologies merged with Microlight3D. Welcome, gentlemen.
Very good. Well, first of all, thank you, Tiffany and Naim, for organizing this seminar this morning. I'm very happy to be in a position to present you this tool. So, you explain where this product line is coming from. SmartPrint UV, developed by Microlight3D. Microlight3D is a company that is headquartered in France, actually in the Alps, and it's a company employing a number of engineers and holding patents related to specific nanofabrication technologies. Has been there for about 5 years now. The founder is a previous founder of another company in the laser domain. And we've been basically developing these tools in the past 5-6 years, and we have exported these tools worldwide, actually. So we're very glad to show you this morning to talk about SmartPrint UV, that you will see is actually a second generation tool in the field of maskless lithography. I am myself based in Canada, so I am in the time zone for the US market. So maybe I would suggest that Julien, you go ahead.
Yeah, sure. So thank you, Christian, for the introduction. So, as Christian said, today we're going to speak about one of our product range. So the SmartPrint UV, which is a maskless lithography system dedicated to rapid prototyping and customized microstructure fabrication. I'm going to skip this part because, Christian, already explained it to you, introduced it to you. So speaking about optical lithography, I'm pretty sure that most of you perfectly knows how does this technology works. However, I would like to give you some basics to make sure that we are all on the same page. So optical lithography is the most commonly used technology to fabricate microstructures for research purposes, but also for production purposes. And I would say that the mostly used technology to do so is the mask aligner system, where the photosensitive resist is exposed with a UV light source through a mask. What we call a mask is a piece of glass, a physical system, a physical component made of a piece of glass with a very thin chromium layer on top of it. So these mask aligner are very perfectly suited for fabricating structure with micron resolution, to do alignment steps in order to align different levels of structures, and also perfectly suited for I would say, they have actually a very high throughput when it comes to fabrication of 4-inch wafer or even higher surfaces. However, when it comes to flexibility, typically for doing, I would say, customized microstructures or rapid prototyping, it's not the ideal technology to use for. The reason why is because by using this hard mask, so this piece of chromium and glass layer, it has to be fabricated prior to be used with the machine, which means that before to go from your idea to the fabrication of your substrate, you have to pass through different steps, such as the design of your image, but also the ordering, the manufacturing, and also the shipping of this mask by a third part. And finally, you can do your lithography, which means that if you have an idea and you want to fabricate, to go to the sample fabrication step, you have to wait few weeks and sometimes later, longer time, and it can be time and money consuming. And also, the last critical point with this kind of hard mask is the fact that once you get your mask, you get a static design, which means that if you made a small error when designing your mask, or if you want to change your design, you have to go back to the full process of designing, ordering, etc., etc. So it can be time and money consuming when it comes to rapid prototyping and customized fabrication of microstructures. So nowadays, our customers are looking for alternative technologies, and especially two main points for this kind of technologies. Being able to fabricate customized 2D microstructure, but also being able to align this microstructure on top of prefabricated structures by a very flexible, more flexible way that what you can do with a mask aligner. And so what we propose at Microlight3D is the maskless lithography system that is based on a spatial light modulator. So how does it work? I would say that in terms of physical and chemical working principle, it's exactly the same as a standard photolithography system. So the idea is that we're going to use a UV light source to project an image and to expose a photoresist that is deposited on a substrate, and using a projection lens. However, instead of using a hard mask, we're going to replace this hard mask by what we call a DMD. So this is an optoelectronic component that, so DMD stands for digital micromirror device. And as you can see on the inset, it's the DMD is actually a matrix made of a small micromirror like this. So these micromirrors are square mirrors with 5x5 micron dimension. And on this DMD component, we have a bunch of about 2 million of these small mirrors. And by controlling the state of this micromirror to be on or off, as you can see on the inset, so in the middle, this is the on state of the mirror, and here this is the off state. And so by controlling this on and off state of the mirrors, you can actually project an image that is composed of black and white pixels. So you can see here on the sketch on the top left corner, your design will be composed of black and white pixels, and by controlling the state of the mirrors, you can control each mirror to be on, and so to project a white pixel, or to be off, and so to project a black pixel, and so to block the light. And so using this DMD, we're going to spatially modulate the light coming from the light source to reproduce the image and send it through the projection lens and then focus it on the surface. So that's the way we actually expose an image. And by using this DMD technology, it means that we don't have anymore a static design, but we now have access to a dynamic mask. Because by a simple click on the software, you can reconfigure the state of each individual pixel and so change the image that is projected on the surface. So it really gives you a shortcut from the design to the fabrication of the sample. if you consider, I would say, if you consider the whole fabrication process, so really from the design to the sample fabrication, it's a way faster than if you have to go by with standard lithography, where you have to fabricate a hard mask and etc. So it's more flexible and it's faster. So this is the way we project an image. And you can imagine that 2 million pixels, 2 million of these small pixels won't be enough to expose a full 4-inch wafer. So how do we control the exposure of larger surfaces? By actually using motorized motorized stages, sorry, that are installed in the machine. So how does it work? When you load your image, so it can be a GDS file, DXF, or very simply a PNG image, so a bitmap image. When you send the image to the machine will automatically calculate the size of the drawing. So as you can see on the bottom left side, and calculate if how many exposure fields are needed to complete the exposure of the design. So as you can see here, the red square correspond to the individual exposure of field of exposure. And you can see that, for instance, for this design, you will need 16 different exposure. And the exposure will be done using a raster scan exposure method, as you can see in the middle, which means that the software will go to the position of the first subimage to be exposed, expose the subimage, then move to the second position that corresponds to the second image to be exposed, expose the subimage, etc., until you reach the last subimage to be exposed. And by doing so, we are able to fabricate structure with micron resolution up to 4-inch wafers. So this was for the working principle. Now, how does the machine look like? So you got here a picture of the machine. So you can see that it's a very small device, a small system. So actually, it's a tabletop system. You can see the dimension are about 52 by 52 centimeter. So it's a tabletop system, and with a very small footprint. And the machine will come with different modules. I will go more into the detail later. And of course, the machine will also come with the dedicated software. So our software is called FAOS, and will be used for controlling the whole process from loading your design to the exposure of the design and alignment step, etc., etc. So I told you that the system is modular. So the same packaging will offer different version of the machine. So actually, we propose 2 different versions: the standard version and the advanced version. So regarding the common specifications, so both systems are based on the DMD technology that I presented you. They are both using 385 nanometer light source, so UV light source, to expose the resist, which means that they are compatible with broadband photoresist, of course, but also I-line, such as SU8. And the machine is also, so both machines are also equipped with secondary light source at 19 nanometer, which means that this secondary light source will be useful when it comes to, I would say, focusing or microscopy or even alignment steps. But I will go more into the detail later on. And finally, the last common feature is also the minimum feature size that can be patterned with the machine, which is 1.5 micron. So how does the difference come from between the standard and the advanced version? Actually, the difference comes from the motorized stages that are installed on the machine. So for the standard version, you got a step-by-step motor stage. And for the advanced version, we have a linear motor stage. And that's really make the difference for different features. For instance, the maximum exposure area. So you see that you're going to have a larger writing area for the advanced version, up to 110 by 110 square millimeter. You can also process larger substrates, so up to 5 inch by 5 inch with the advanced version. One of the key points also is the repositioning accuracy, which means how good is the positioning of the stage, which is a really critical point when it comes to the raster scan exposure method, because we're going to expose subpart and then stitch the subpart to each other. And the quality of the stitching will be given by the repositioning accuracy of the stage. So you can see that for the standard version, the accuracy varies from 1 to 2 micron. And for the advanced version, it's way better because it's 250 nanometer. So in the case of the advanced version, we'll have almost no error in terms of stitching. And finally, one of the also most interesting feature, the most different feature between the standard and the advanced is the writing speed. Okay, because the writing process will be given by the speed of the writing process will be given by the time of exposure of each subimage, but also the displacement time between each subimage. And by using a linear motor stage, you can go faster, and so you can print faster. So you see that you can have a difference, a factor of about 2 to 4, depending on the condition of use, between the standard and the advanced version. And as I said earlier, in terms of packaging, the machine will be exactly the same in terms of dimension. So you can choose between standard and advanced version, and then you can also choose different options. And one of the main options is the projection lens. So as I told you, the image will be projected through the projection lens and focused on the surface of your sample. And this is the way we're going to do the exposure. And so the machine comes by default with a 2.5x objective, which gives you a writing resolution of 6 micron. And you have access to 3 different options: the 1x objective for lower resolution, so 15 micron. And if you want to go higher in resolution, you can go for the 10x magnification objective, which gives you the 1.5 micron resolution. So you can see the higher, of course, the higher the magnification, the higher the resolution. So those objectives can be manually removed and exchanged, and in about a second, using our dedicated magnetic ring that are installed on the machine. Okay, so that was for the specification. Now I would like to show you some example of structure fabricated with the system. So I'd like to start with some results done with the 1x objective. 1x objective. So typically 1x objective is really interesting when it comes to patterning a low resolution structure, of course, and a large area of large structure actually. So you get an example on the left side of a typical microfluidic channel. So this one is made of three different actually channels. 2 channels for the green component and 1 for the red component. So the typical dimension here are hundreds of microns for the width of the channel. And here you got the result of the PDMS molded on the master that has been fabricated with the machine, and then filled with the different different components. So this is really useful to use the 1x when it comes to microfluidic, because most of the time you will need to pattern large surface with low resolution. Another example is this wireless, this wireless stretchable surface acoustic wave-based temperature sensor here that has been fabricated on a silicon substrate and then transferred onto this EcoFlex/Solaris substrate, which is, as you can see, a stretchable and transparent substrate. So here typically, the pattern has not been fabricated directly on the stretchable substrate, but they have been transferred using a stamping method from the substrate, from the silicon substrate onto this stretchable substrate. However, it's possible to work directly on transparent and non-flat surfaces. So 2 examples here. So here you got an example of a Parilene foil that has been patterned using, actually that has been covered with a graphene layer and then covered with a pattern with these electrodes here. So this is used this is a patch used for wound care application. And you can see here that the substrate is transparent and also non-perfectly flat. It's a flexible substrate, so there was some defects in terms of flatness of the substrate. And actually, we can work with very easily with this kind of substrate because the objective that we are using with the machine, they have a very long working distance. So from 2 to 3 micron, from 2 to 3 centimeter, depending on the objective, which means that we have a non-contact working system. And also, there is a large working distance, but also a very deep depth of field, which means that the focus of the image will stay correct in a certain thickness of the optical waste. And so in this case, working with the 1x, you have a depth of field which is about a few hundreds of microns. So if you have any defect on your surface, they will be compensated by using this low resolution objective. So another example also on a flexible substrate. So here you got an example of a ring-shaped metallic micro heater here, which has been fabricated on top of a polypropylene foil. And this one are used typically for strain-tronic with 2D materials. So our customer are doing this micro heater, then they transfer 2D materials in the middle of this micro heater, and then they look at the optical properties when stretching the material by increasing the heat, the temperature of the polypropylene locally with this micro heater. Speaking about another objective with low resolution, the 2.5x objective is also a really good compromise when it comes to resolution, because the writing resolution is about 6 micron, but also to work with very thick resist. Once again, the 2.5x objective have a long working distance and also a long depth of field, also more than few hundreds of microns, which means that you can work with very thick photoresist. And it can be really useful when it comes to microfluidics, because you need to work with few hundreds and few hundreds of microns of photoresist, and most of the time with resolution that are about tens of microns, or maybe even less, or even I would say more. So a few hundreds of microns, few millimeters. So you got some example here of a microfluidic channel made in SU8, and 2 examples here of a cell sorting device. So you can see that the wall are very steep, and so with a very good quality. And by using this high depth of field objective, we can also reach very high aspect ratio structures. So on the bottom side, you can see that on this 90 nanometer thick resist, we can reach 8 micron structure, so which give you a 1.10, 1.11 aspect ratio. And we can also do very thin structure here, 35 micron pillar on a 300 micron structure, on a 300 micron layer. So this can be really useful, when you have to work with high aspect ratio structures. Okay, so now going more a bit into resolution. So a few examples of the 5x objective. So here, just an example of contact electrodes with multiple layers that have been fabricated for spintronic application. So here you can see the different layers between the different color between the different layers here, and the channel here are just few tens of microns. Another very fancy example, this one. So for those of you who already heard about the Tour de France, it's a very famous cycling competition that occurs every year in July. And so in 2017, the Tour de France was passing by Grenoble, where the company is based. And so one of our internship was really into this cycling competition. So he designed this small map, and then he exposed the map, and then he fabricated actually the map with a micron scale resolution. So this is just to show you how easy it is to go from your design, from your idea, to something concrete, to something real, to a real sample fabrication. So in a few hours it was made, and it's really easy to use for students, for instance. And finally, digging into more resolution. So a few more examples of the 10x objective. So on the left side, you get an example of an interdigital transducer structures that are composed of 2 micron wide lines with 2 micron wide lines and 1 millimeter long, and they have been made in copper foil after lithography and etching, and they are used for surface acoustic wave sensors. And one more example here, it's also contact electrodes for typically working with 2D materials. So the idea here is to transfer the 2D materials here, or actually to deposit to fabricate this contact electrode onto material that have been deposited here, and here, And the details here, sorry, I just missed the inset, but actually the details here are about 1.2, 1.3 micron. So you see that by pushing the limit of the machine, you can also go a bit under the resolution that we give, which is 1.5 micron. That was for some example of fabricated structure. Now I would like to highlight one more feature from the machine, which is the alignment. So I told you earlier that the machine comes with a secondary light source at 590 nanometer. And the machine is also equipped with a feedback camera. And by coupling this feedback camera with the secondary light source, you can do alignment steps. So how does it work? So actually, instead of using the UV light source, we're going to use the yellow light source to project the image on the surface. And by doing so, you can see actually the surface of your sample. And if there was something written on the sample, you can see the pattern on the sample. And also, in the meantime, you can see the pattern that you are projecting on the surface. So if you look at the sketch here, so in green is the sample with already patterned electrodes. And what you're going to see with the feedback camera is this electrode here in yellow. So this is the pattern that you have fabricated during the first lithography. And then what you can see in black here, the black dots, represent what you're going to project, so what you want to align on your first layer. So you see that it's really intuitive because you see both the substrate surface and the image that you want to project and align. And so the machine comes with, the software comes with two different modes. So the free mode, I'm going to show you what is it useful for, and also the semi-automatic mode, which is a more standard mode where you're going to give coordinate of alignment crosses to the software, and the software will do the job to calculate the position and to align the overall design. Free mode is really useful when it comes to aligning a very specific, I would say, area of interest on your substrate. And the typical example of this alignment mode is aligning contact electrode on 2D materials. So we have plenty of customers working in this field. The idea is to put contact electrode on top of material that has been randomly deposited on the surface. So these 2D materials has random shape, random size. They have been randomly deposited on the surface. So this is really interesting to work with maskless lithography system because you have to, for every new sample, you have to adapt your electrode to these new flake materials. So this is really useful for that, but it's also really useful when it comes to alignment, because by using the free mode, you're going to project the image of your electrode. So let's say this part, and you're going to also see the image of your substrate, so where the flakes has been deposited. And by simply moving the projected image on top of the surface, by using the XY motorized stage, you can align perfectly your flakes with the electrode and so fabricate the structures. So yeah, once again, here's some example with different materials. So molybdenum selenide, gallium selenide, graphites, boron nitride, and a recently published example of one of our customers working in the University of Nevada. Here they have been, they use a stamping technique to create this kind of layered structure, so made of different 2D materials, and then they do this contact electrode to measure optical or electrical behaviors. Another example of aligned structures. So here you got for structure for spintronic application. So the pillars, the triangular pillar has been fabricated using lithography on a tantalum oxide layer, and then followed by etching step. And then the gold contact here has been aligned, lithographed, and finally etched by metal lift-off on a gold layer. So once again, it has been used with the free alignment mode, because here there is just a few area of interest to align. And here you get a typical example of a larger surface that has been done using the semi-automatic mode. So here, in this case, the customer use alignment crosses that are being placed in different corner of the substrate, and they use these different alignment crosses to pattern and align different layers of this heater sensor platform. and that has been fabricated once again with lithography alignment and etching and or etching or lift-off process. Regarding the resolution of the alignment, here you got a typical example of what we can do. So here you got two different layers. The first layer, the orange layer here, which has a cross shape, is the first layer that has been fabricated with the system. So it has the stripe are 10 micron wide, and the second layer in yellow here, made of this four line with this small island in the middle, has been fabricated followed by a alignment step, and you can see that the typical error that we can reach with the machine is about 1 micron. So this is for the standard, for the error for the advanced version. And finally, regarding alignment, you can of course do what we call mix and match. So you can, for instance, fabricate structure on a device that has been fabricated with, for instance, e-beam lithography. So you can imagine to fabricate your very small structure, the most result structure with e-beam lithography, and then switch to smart print to fabricate the low resolution structure with another objective from smart print. So you will gain some time, because of course using e-beam to do very large pattern can be really time consuming and of course money consuming. So here you're gonna have really a gain of time. But you can also do mix and match with the same machine. So which means that you can use two different objectives from smart print to do mix and match. So this is a typical example of what you can do. So here in black, you got the first layer that has been fabricated using the 2.5x objective, because it contains the lowest resolution pattern, so the contact pad. And on the second step, the customer used the 10x objective to fabricate this red layer, which actually contain 6 different interdigited electrodes, like you can see here on the right side. And by doing alignment and exposure with the 10x, they can contact both different layers, so the 2.5x objective layer and the 10x objective layer. And so you get the results here, and here the inset. This is what I showed you earlier. So yeah, that was typically for some example of lithograph structures and also of line structures. But you can imagine to use the machine for many other application fields. I mean, as soon as you need to fabricate microstructure, it's going to be useful. So it can be for biotech application, for microelectronic application, optics, or whatever comes to your mind. So as a conclusion, I would say that Smart Print UV is a perfect solution when it comes to rapid prototyping and customized fabrication of 2D microstructures. It has a very versatile and intuitive alignment module. And of course, it's compatible with all the standard photoresist, including highlight photoresist, and works with not only standard substrate like silicone or glass, but also with a large variety of substrate that can be flat, not flat, flexible, transparent, or any kind of material, large scale substrate, of course, to 4 inch or even 5 by 5 inch, but also very small substrate like 5 by 5 millimeter. So it's a fast, user-friendly, and affordable system for doing rapid prototyping. Yeah, and I thank you for your attention.
Thank you very much, Dr. Cordiero. And at this time, we will take questions from the audience. Please know that special permissions have been put in place to disable your camera and your mic. So you have two options. You can either put your question in the chat, the Q&A chat, or you can raise your hand to speak, and we will entertain those now.
Thank you, Tiffany. Julian, I wanted to ask about the standard system. You mentioned that the field stitching accuracy is in the order of 2 micrometer, and that is basically about the same as what the resolution of your highest objective lens. So how do you mitigate that discrepancy?
Yeah, that's a good remark. So, so yeah, as you noticed, the accuracy is the same order of magnitude as the minimum feature size. So how do we manage that? I would say by working with the advanced version. And the other option, of course, would be to, if you worked with the standard version, there is few tricks to know about the exposure. So typically, one thing you can do is by when working with GDS or DXF file, you're going to have to convert this file because the machine will not work directly with this format file. Okay, it has to be, it needs a bitmap kind of bitmap file format. So we have a conversion module that allows conversion from this CAD format file into bitmap file. Okay, and by doing so, you will have some different parameter to select. And one thing you can do is to you're gonna have a grid that show you where the slicing of the image will happen. So by having this information, you can move the slicing grid onto the design to avoid cutting the very sensitive structure. And so that one of the trick that you can use when converting a design. Because of course, if you have a stitching error of about 1 to 2 micron on a few tens of micron structure, that's the impact will be less important than if you have a problem with a small feature. So that's one of the idea. And there is also some other option, like typically adding some overlap between the sub-images. So when we calibrate the machine, what we do is that we make sure that the connection will be the best one between the sub-images. So there will be no gap and no overlap between the sub-images. However, with the standard machine, sometimes to avoid this kind of error, you can add, using an option, you can add a small overlap between the images. So it will change a bit the dimension of your structure, but it will also ensure to have no gap between the different parts of your sub-images.
Thank you. I have one more question really fast. You had an image of SU8 structures, I think 300 micrometer thick, really high aspect ratio, and you can see how it is tapering down a little bit. Is that actually from the system focus, or it's an SU8 processing related feature?
Yes, so actually for the this image, actually just this is just few tests that we have made with very high aspect ratio structures. So I think in this case it's probably yeah, it's just probably due to the fact that we are trying to pattern very small feature in this case, and with such such thick resist, the problem occurs. But this will not be necessarily the case for all thick resist. Actually, this is really typical from this structure, but this is not representative of what we have. Once again, using the 1x and 2.5x, the depth of field being way bigger than the thickness that we can pattern, or actually the same order of magnitude, yeah, you should have a very steep structure. Here in this case, it was just to show you that we can go also with high aspect ratio with thick resist, but of course it's not perfectly representative of what we can do. We can do much better things, but it was, I would say, a very extreme structure for the system.
And we do have a question in the chat. The question is there any resistant residue? I assume it depends on multiple factors. However, do usual post-exposure photolithography steps address any residue?
I think if I understand correctly the question, there will be no residue. If the question is there any residue around the structure, I would say no. I mean, this is a go, no go. I mean, the resist will be either exposed or not exposed. So I don't know if it was exactly the question, but I would say no. I mean, there will be no post-processing needed. I mean, by using the correct exposure time, there will be no residue remaining on the surface.
Thank you. Yes, and Dr. Young has confirmed that you have answered his question.
Okay.
Thank you so much for joining us today, Dr. Cordiero and Christian, and thank you, attendees. Have a nice day.